Welcome back. We're starting to study a new chapter here, and we're going to talk in this chapter about studying rational equations and expressions. And what we're going to start with is rational expressions and how to simplify those things and hopefully work towards solving rational equations. A rational expression, we think of a rational number, is a number that is a p over q number. So like 2/3 is a rational number. 5/7 is a rational number. 7/5 is a rational number. A rational expression is one that has polynomials on top and bottom. So I could have something like 2x squared plus 5x plus 7 over 3x squared plus 7x plus 5, right? Using the same coefficients. This is a rational expression because it is a ratio of polynomials. We're still going to have to use factoring for a lot of this. So if you're not solid on factoring, I would go back to the last unit and study those factoring methods. I've got those listed here. If any of these don't seem familiar to you, go back a video or two and try and review that factoring method. So as I said, a rational number is a number that's written as a fraction. It's a ratio of two integers, p over q, where q is not equal to 0 specifically because we don't want the denominator to equal 0. We can't divide by 0, and that's the main overruling rule of math. That's the one rule that doesn't go away. The same way a rational expression, as I said, is an expression of polynomials written as a fraction, and the same rule applies. We don't want the q, we don't want the denominator to go to 0. So we don't want x squared minus 4, we don't want it to equal 0. To evaluate a rational expression, you're going to do this much the same way that you would your regular polynomial expressions. When you evaluate, you're looking for a number answer. You're trying to evaluate for some x value that you know. On this first example, x equals 6, we're given this polynomial, this rational expression, x over x minus 3. So I want to do 6 over 6 minus 3. 6 over 6 minus 3 is the same as 6 over 3, which is equal to 2. Second example here, for x equals negative 3, I'd say negative 3 over negative 3 minus 3. That'd be negative 3 over negative 6, which is the same as positive 1/2. For x equals 0, I would have 0 over 0 minus 3, which is 0 over negative 3, and 0 over any number is just 0. And finally, for x equals 3, I'll change colors to red, and you'll see why in a second. When I try and evaluate 3 over 3 minus 3, I get 3 over 0. And remember the rule back here was that the denominator, q, cannot be 0. So this is actually undefined, because we can't divide by 0. And what that tells us is that these rational expressions have some restrictions. We can sub in a lot of numbers, we can evaluate for a lot of numbers, but there are numbers that we cannot evaluate these rational expressions for many times. And those numbers are numbers that make the bottom 0. So notice, since 3 minus 3 is 0, in the denominator, 3 is a restricted value. X equals 3 is a restricted value. We also call those restrictions a lot of times. All right, take a second and try these. I'm going to erase and show you my answers in 3, 2, 1. This is what happened when I evaluated for 2. I got negative 1 over 7. When I evaluated for x equals 0, negative 3 over 5. When I evaluated for 3, I got 0 over 8, which is the same thing as 0. And when I evaluated for negative 5, I got 8 over 0, which is undefined. That tells me that x equals negative 5 is a restricted value. For these problems, typically what you'll do is from the beginning of the problem, you'll say, we don't want the denominator to equal 0. We'll try and find the restricted values from the beginning. So I would say x plus 5, I don't want that to equal 0. And then I can solve that and get x is not equal to negative 5. x is not equal to negative 5. That is your restricted value. So before I even started the problem, I could have told you that x cannot equal negative 5. Here's another example, the expression x over x plus 3. If I wanted to find the restricted value, I would say x minus 3 is not equal to 0. I would add the 3 to both sides and see that x cannot equal 3. 3 is the restricted value. It's undefined for x equals 3. X equals 3 is a restricted value because 3 makes the denominator 0. Let's try and identify the restricted values here. If we're asked just for the restricted values, all we have to do is take the denominator, 2y plus 7, and say that that thing is not equal to 0. And then try and solve it just as we would an equation. Divide by 2, and y is not equal to negative 7 over 2. Sometimes it's as easy as this, where we just have an x in the denominator. X is not equal to 0. It's already solved. X can't be 0 because 0 would make the denominator 0. When we have one that's more complex like this, we still do the same thing, but we're going to have to do a little bit more work. A squared minus 25 is the denominator. Find the restricted value. We would say a squared minus 25 is not equal to 0. And then we can try and solve this as we would a polynomial equation. First, we get the whole thing equal to 0. Second, we factor, and hopefully you remember this is a difference of squares. And so with each piece, I can set equal to 0. A is not equal to 5, and a is not equal to negative 5 because those make each of those 0. Notice that each of these make the original denominator 0. 5 squared minus 25 is 0. Negative 5 squared plus 25, also 0. You do have equations, like in example B, where I would say the denominator, x squared plus 9, not equal to 0. But there's no way to factor this. This thing right here is prime. And since I can't factor it, and I can't find numbers that make it 0, we might instinctually say maybe negative 3. But negative 3 squared plus 9 is 18. That means that there are no restricted values. There are no values, no real values anyways, that are going to make the denominator 0. These restricted values are restrictions on the domain of the function. So when we get ready to graph these rational expressions, we're going to see that when we graph them, the domain is going to have something out of balance at those points. We'll have a discontinuity at those points because the domain has a gap. To simplify rational expressions, what we're going to do is factor the numerator and denominator as much as we can, factor it into prime factors, and then anything that matches up top to bottom will divide away to 1. It helps to start with just a regular fraction first, just to see as an example. So 21, if I broke down 21, that's the same as 7 times 3. If I broke down 35, that's the same as it's the same as 5 times 7. And then since I have a 7 in the numerator and denominator, those will divide away to 1, and I'll end up with 3 over 5. The same thing happens with rational expressions with polynomials in the top and bottom. So this example, simplifying this rational expression, if I factor the top, it would be a GCF of 2. I could factor the bottom by difference of squares. And notice that I have an x minus 3 in the top and the bottom that I can divide away to 1, and I'll be left with 2 over x plus 3. That's my simplified version of that rational expression. Try this one. Very similar to the last one. You could factor the top by GCF, the bottom by difference of squares. Notice you have a p minus 7 top and bottom that you can divide away. You'd be left with just 2 over p plus 7. Those two divide away to 1. All right, this is not any more complicated. We just have to do a little more work to find out what the prime factors are. Let's take 18 and do a factor tree. It's 9 and 2, which is 3 and 3. So I have 2, 3, 3, and I have 4 A's. On the bottom, 9 is 3 and 3, and I have 5 A's. Divide away anything that matches up. So A. I've got a 3, I've got a 3, and the only thing left on top is a 2. the only thing left on bottom is an A. If there's nothing left on top, or if there's nothing left on bottom, we just leave a 1 because we're talking about multiplication and division here. If you divide away all the factors, you would just be left with a 1. All right, these get a little bit more complicated, but it's the same idea. We're still going to just factor the top, factor the bottom, and try and find things that divide away. One of the common mistakes is shown here. Since we have C's, a lot of people would like to say C over C. That leaves you with a C. You cannot do that. You have to take away an entire factor at a time. So the example that we saw in the last slide, if we could factor it, the top we could factor by GCF. The bottom we could factor by star method, so I'll go do a little scratch work over here. I would have 10 and 10. A times C is 1600. The bottom is negative 80. And I need things that multiply to 1600 and add to negative 80. I'm doing some division now. 1600 divided by 100 is 16. That's not quite going to work. 1600 divided by 150 is 10. That's not going to work. 1600 divided by 16 is 80. 1600 divided by 32 is 50. That's very close. Oh, I missed the, this is a classic, I missed the easiest multiples. Negative 40 times negative 40 is positive 1600. And negative 40 plus negative 40 is negative 80. But I also made a mistake from the beginning. There's a GCF in all three of these. That's going to make our work a lot easier. So let's do that first. Let's first say we could take a 10 out of everything and have left C squared minus 8C plus 16. And now my star method is going to look a little different. So here, this star method, I'll have a 1, a 16, and a negative 8. So now negative 4 and negative 4 multiply to 16. Negative 4 and negative 4 also multiply to 8. So this would be, I'm going to leave the top alone for a minute, 2. C minus 4. The 10 I'm going to break down into 2 and 5. And I would have C minus 4 and C minus 4. That's that star method that I got that from. Do you see things that match up? We should see a 2 and a 2, C minus 4 and a C minus 4. I'm left with nothing on the top, and remember I said if there's nothing left, we're going to leave it as a 1. And on the bottom, a 5 and a C minus 4. All right, let's see another. This is another example of just a trick that we can do. So if we could take out a GCF of 3 on the top and have C minus D. And we have almost the same thing, but we can't get rid of those because they're not exactly the same. But if they're in the wrong order, here's a trick that you can do. We'll leave the top alone, and we'll factor, to get this order to flip around, we're going to factor out a negative 1. Negative 1 out of D would be a negative D. Negative 1 out of negative C would be a positive C. And notice that did make those match up now. And so I'm left with 3 over negative 1, which is just equal to 3. Negative 3, I'm sorry. All right, another example like that, you should try this. It's going to work very similarly. I'm going to start showing you my answers here. If we factor the bottom using difference of squares, notice we have a y minus 5 and a 5 minus y. They're almost the same. If we take a negative 1 out of the top, it'll make a match. And then we can eliminate the y minus 5s. And what we're left with is negative 1 on top, y plus 5 on bottom. That was the last example. That's simplifying rational expressions. The next thing that we're going to look at is adding and subtracting rational expressions, and then multiplying and dividing rational expressions.